Okay, can everyone hear me and see my screen?
I see your
Yeah.
screen again.
Yes, thank you.
All
Yes,
right.
yes, I see.
Okay, I'm an amateur astronomer in Massachusetts, United States, and I've been, like most of you, playing around with exoplanets, observing, recording light curves, posting data, and I guess you can say evolving as I learn how this works. I would also like to introduce my co-PI, Arden Burdenoff. He's an astronomy student now in postdoc at MIT. He works on a speculus project. We kind of did this together as an experiment. For me, it's like a hobby. And this is the story that I'm going to tell about how this evolved. First slate. This is my first slate, I guess you can say, when it comes to exoplanet observing. 2013, my first observation trying this was WAS3b. And so you see here my first entry as WAS3b and the light curve. And this is the first time I ever attempted any kind of photometry, because before that I was trying astro imager, for aesthetics, nice pictures and stuff. But where I live here, it's kind of moderate light pollution. And so I kind of there's no way I can do that well with that. So I tried this. And so right now I have over 100 entries in ETD. And so I would really like to thank Exoplanet Transit Database for the opportunity to upload data, because I think that's really helps an amateur to get either auto feedback from the fitting and the pictures posted on the web page, and so it just kind of took off for me. This is my setup more or less. Basically, it's a resident place. The house is actually, the telescopes are facing my house. The telescope on the right side is a C14, 14-inch aperture telescope. I use that one for follow-up. Mostly now I use it as a TESS follow-up observer in the TESS SG1 group. And so I go after their candidates, record the light curves, upload it to their database. The other telescope, well, first started out experimental, is a RASA wide field telescope. It's 11 inches. And this is a survey telescope. That's how I use it. A close-up of the RASA telescope. You see the FLI camera attached to the front. So this is a wide field attached to the front as opposed to attached to the back. So this type of telescope design, that's how you get the very wide field optics with this. Okay, GPX survey equipment. This is more like what you see more as the specs. The RASA 11-inch, very fast F ratio. First, I tried out an ST8300 camera, and then later, as we upgraded, then I went with the twice the image area of the ML16200 camera. A mount, you need some sort of mount that's for, at least for the RASA 11, at least 60 pounds capacity. Control software, I use software BIS, the SkyX, CCD commander to do the multi-targeting. There's a RC filter in between the camera and the RASA telescope. The processing software, which is very important because I didn't really know how to do this. This is Artem developed this, and I'm in Acton, Massachusetts, which is like a 45-minute drive outside of Boston, Massachusetts. I always get this question is, okay, how do you store these things? So it's actually kind of complicated and evolves over time. Basically, the covers are telegizmos covers that you can buy, but inside it's like 2 layers. So there's an inner layer covering to try to seal from moisture, and then the outer cover, which you see here, protects rain from getting in, but there's still moisture that gets into the telescope, so that's why there's an inner layer. And my biggest nemesis I have to deal with are actually mice chewing through different things, and so I have to chase them out and all that. Okay, the GPX. GPX started as KPS. Artem was playing around with the master telescope and doing some master telescopes, also a wide field telescope in Russia. And he was imaging certain fields in the Milky Way galactic plane. And I was trying different things. And before that, what I did is just aimed like a prototype RASA telescope into a different field. And what happened there is that KPS-1b was sitting there. And so we discovered that. And so that inspired us to go further. And so the goal of GPX is to use amateur equipment to survey high density star fields, which you'll find in the Milky Way galactic plane for the hot Jupiter type exoplanets. Just a reminder that we're using the transit detection method to see these. Just like as you follow up to see if there's any existence of a possibility of an exoplanet. Most of the time what you get though are false positives, probably like 95, 99% of the time I would say, binaries and other things, so we have to sort those out. Okay, KPS-1b, I call this a very serendipitous discovery because you see the little white box. That was the field of the RASA telescope. I aimed at one spot. I just randomly picked that spot. Maybe one person can say it's like, okay, maybe I used the Big Dipper as aiming stars to point to it. But I mean, this is what you call like pure luck that there was an undiscovered exoplanet in that field. And so that's what kind of got all this started. This is the discovery light curve. So from the RASA telescope, and this had the 8300 camera on it. And this is the light curve after processing through Artem's pipeline. And so you see in the center there, that dip, that characteristic dip, which could be a binary or an exoplanet. And so then there was a lot of follow-up observations to this to try to sort that out from different professional and amateur astronomers and many from ETD. And so after the validation, like you need Sophie from OHP did the radial velocity measurements, and based on that, this transit thing candidate was a hot Jupiter. And so that's, you know, we were kind of surprised. It's like, wow, that was fast. We actually found something. And this is the discovery paper. And if you look at the authors, they're pretty much from different parts of the world. A lot of ETD observers, professional astronomers, and even the journal itself cited that this is one of the papers that was like truly international. From KPS-1b, we upgraded the survey. That's when I switched to the more expensive 16200 ml camera. That had a double the field, and then we experimented with trying to get more, you know, survey more fields. So this is what we use software so the telescope would move to 4 different fields, and then like keep on imaging the 4 different fields. from a science point of view of this survey, what we tried to do is, with better resolution compared to the ground-based surveys, that maybe we can see something that other surveys may not, because we have better resolution, and maybe there's something there that would otherwise be blended. Blended means two stars close together, and maybe one star has a transit and the other one doesn't. And so what happens is, if you're doing photometry on the two stars close together, the transit would have a lot lower depth, which then would kind of fall out of the range of the ground surveys to detect them. This is using CCD Commander, what the image sequence is on the telescope. So there's 4 fields. For each field, we take 3 images, like a target 1, 3 images. They're 40-second exposure lengths, and then that you would move to an adjacent field 2, field 3, and field 4. And so you would do this. You would the RA would be the same for the 4 images while you're changing the deck, so that it's easier on the telescope, especially when you get close to time to do a meridian flip. And so with this sequence, each star in the field will be looked at with a cadence of 10 to 12 minutes. And the goal was to observe for 3 or so months. And the minimum goal was to have 150 hours collected for each field, and then the data to be processed. The first discovery, as we're in the GPX survey, looking at the galactic plane, is GPX-1b. This is what the RASA telescope saw. You can see again in the middle that dip. And so this became, a candidate, just like we like to see this dip. And then we sent the candidate around to different observers to try to validate this. And validation involves, you do photometry and different filters. Like somebody would do a red filter, someone do a near infrared filter like an I or I prime, V filter, blue filter, or a G prime filter, and see if the transit depths are all the same. That you want to get through that. That's your photometry validation phase. And then after that, then a telescope like the SOFI spectrograph would agree to observe the star after we do our initial validation. What is very interesting about GPX-1b is that TESS could not detect it with their auto transit detection algorithms. So they have like SPOC as one of their auto detecting methods, and QPS, and neither of them could see it. And we kind of rushed to try to get this published, and we consulted with the TESS group to make sure that, it's like there's something there and we'd like to collaborate with you. And but at the same time, we were actually fearful that they're going to get it detected before we can publish. But if you look at the image here, the left image is what RASA would see. The right image is what TESS would see. So you can see that the brighter star that's close by, the GPX-1b, pretty much just blurs it out. And the only way that TESS data can detect it is with a more customized software that does pixel type of photometry. So if you use pixel photometry placed right where GPX is, then you can see some evidence of a transit. And the TESS group actually did that for us with their specialized software to verify that what we're seeing is true. And so then after RV validation by SOFI, GPX-1b turned out to be a brown dwarf, a smaller size brown dwarf, a little bit above the 13 mass Jupiter mass. And so these are actually rarer than hot Jupiters. And so it has a high scientific interest. And for a lot of the analysis done by professional astronomers, the age of the GPS system is kind of young. So like for brown dwarfs, their radius tends to be similar to Jupiter or one Jupiter, but the radius of the GPX-1b is larger, 1.4, so it's either inflated, the atmosphere is inflated, or as being a younger developed thing, the planet may not be to its final radius. It's still developing. Looking at lower mass brown dwarfs, this is a recent publication by Greaves, and you can see the HAT 70b, that's a 12.9 mass Jupiter. It's right at that transition between hot Jupiters and brown dwarfs. And then the TOI 1278b, larger. And so GPX-1b at the publication of this paper was the third, smallest brown dwarf for transiting brown dwarfs. And so you can see like Kelt 1b was one of the first that was discovered. That's almost twice the size. And so there aren't many of these. So the other thing is that the period is very short. It's 1.7 days. So this gives a lot of opportunities for follow-up observations to see, okay, what's different about these low mass brown dwarfs compared to hot Jupiter. So there's a lot of research opportunities in the future that people can do. Another type of model are these isochrones that try to peg down the age of the brown dwarfs, and GPX-1b is the red dot that you see in this, where you plot mass and radius. And based on the isochrone there, it's pretty, from this method, it shows that it's a young system. And for the orange line, that's like 50 million years. So there's an uncertainty range of how old the system really is, but this is another piece of evidence that suggests that GPX-1b is a young exoplanet, brown dwarf. This is the discovery paper. What's, I think, the take home looking at the different people co-author on the discovery paper, it's probably an even mix of amateur and professional astronomers from around the world. There's a lot of TESS astronomers on here, people that helped us with this, trying to get a more scientific paper with the different, parameters of the exoplanet. So we collaborate with them, and it, kind of gave us some exposure too. And it helps that I'm a TESS follow-up observer because I knew who to ask for help with this. So, continuing with that, you can see some of the names that professional astronomers big in exoplanets, and the GPX follow-up team with a lot of ETD observers. Karen Collins on the TESS SG1 was very helpful to connect us to the right people to look at different things and get us test data, the custom test data. So we are very thankful for the people that helped us and collaborate with us to make this discovery and help publish. And publishing is that's the most challenging thing from a amateur astronomer's point of view, because there's a high rigor in terms of writing these papers, reviewing, and getting all the information right. The third interesting discovery, and I call this kind of a fun star, it's a pre-cataclysmic binary, where the binary, it's a K star. That's a small K star that has a white dwarf companion that's orbiting very quickly. It orbits like every 7 hours or so. And in the fall, it's a pretty northern latitude type of target. So in the fall, you can get a complete orbit of this, the white dwarf around the K star. And it has transits, it transits, and the transits are only 10 minutes long. They're very quick, and it has very sharp ingress and egress. And so it's interesting, and I'll show you why. First, this is what I saw, discovery phase plot. So you can see here, from the RASA thing, you look at this, it's like, oh, that looks like a binary, contact binary. But that funny dip there is like, okay, what is that? So that kind of, spurred us to try to figure out what that was. Is this an exoplanet? Is what's going on here? So that was really eye-opening. Okay, what's interesting about this is that normally when you have binary transits or white dwarf main sequence star transits, the depth of the transit changes from lower to higher optical wavelengths or filters. And, because one star is sort of red and one star is kind of white. And so you have like a different transit depths. Like I think for a white dwarf main sequence, the blue transits are deeper, and then because the white dwarf is bluer, and so when you go into near infrared, the transits get shallower. That's what you expect to see. But for this particular transit, what happened is the red transits were much deeper than the blue transits, blue filter transits, or the near infrared transit filter transit. So this is like there's something else going on here. And it was particularly deep when using the hydrogen centerline filter in the red. So this is interesting. The other thing is that for this star, that red transit depth changes year to year. So in the discovery, luckily we discovered it at its deeper phase, but in the next year, the transit depth was only half. And then the year after, the transit depth was back to its deeper phase. So the transit depth is always changing with this. So there's some sort of activity, accretion activity going on between the white dwarf and the K star that emits reddish type of light. That's kind of how we feel what's going on here. So this thing is very dynamic. The red dwarf is pre-cataclysmic because it's not fully accreting material to become, nova, but there's a prediction that, like sometime in the future, the orbit will decay enough where it will become that. And also the baseline light curve, the variability of the system changes year to year as well, besides the transit depth. So this is 3 different years, a full cycle of the orbit, and you can see that the shape of the light curve changes. So that's why you have both a transit depth that's changing, and you have a baseline variability that's changing. So that's why this, to me, is a fun star. Every year, you don't know exactly what you're going to get. Okay, in my concluding slide, GPX survey in the TESS era. I guess one of the first things I feared is, are we obsolete now? Like most ground surveys are kind of shutting down, at least the original ones. Newer ground surveys with larger telescopes are, taking their place. And I am still doing this. It's now a couple years later since these discoveries. And so my data processing has kind of changed a little bit. When I process it and get light curves that look like exoplanets, the first thing you do is look at Gaia to make sure the star is like a lower radius type of star, and the transit depth is a possible hot Jupiter transit depth instead of like binary. And then using TESS data, which what I have is a Python program that does the pixel type photometry on TESS cut, like image slices. And so I do that and see if the transit shows up in TESS data. And the better candidates, what seems to happen is that you see that faint secondary transit, that indicates a binary that you would not normally see with ground-based telescopes. And that little faint secondary transit means that it's a binary, so that candidate's been killed. So over the last couple of years, basically all my candidates are killed, and I don't have any new candidates for follow-up observers to do what we did before, because of how the TESS survey, the data, this new modern data, the better, higher precision. We continue, and so the reason why we continue is that we only look at high density star fields, and that is still a weakness of ground surveys, and it's also a weakness of TESS. Just as GPX-1b was discovered, if the stars are close together, maybe the transit would be diluted enough where we can see it, but TESS cannot. But I would have to say our odds of finding another candidate where like a GPX-2b is kind of diminishing over time, but we still go. Besides exoplanet transits, we look for unusual variables, just like what you saw in that white dwarf transit thing, something that just looks unusual. I seen like, probably hundreds of thousands of phase plots. So I kind of programmed myself what to look for as I scan through these things and try to find something that is of interest to follow up on, like maybe a signal artifact or something, which are usually systemic errors or problems with the photometry, but you never know. There could be something there that is really interesting. So there's a lot of hope in this project. There was in the beginning, there is now, but we made progress, and that's where we are. So thank you for listening to our presentation.